either. Okay. All right. So we started chapter 12 last time. Yes. Oh, you can't see.
Yeah.
That would be nice. You can check. Now it's how to focus again. Okay, so we started last time with chapter 12. We covered just a few things. So remind me, what are the three types of probability?
Theoretical, classical.
Theoretical, classical, and
Personal.
personal. Okay. All right. So I'm going to put up a little probability distribution, and I want you to tell me, is this empirical, classical, or personal? Okay. So I've got marital status. Okay. And I've got never married. I've got married. I've got widowed. I have divorced. These are women 25 to 29 years old according to the census. Okay? And so according to the census, I'll put census up there.
Is this actual data or are you just making it up?
It was in the old book, and I don't know. I don't care whether I assume it's real, but I don't know if it's made up. Okay? So, and it might have been true 10 years ago or something. I don't know. So the never marriage of 0.503, the marriage of 0.452, the widows are 0.003, only 2 zeros, and the divorce of 0.042. Okay? So, is this personal, empirical, or theoretical? Should we vote? Who says it's personal? Can't get any more personal than marriage, right? Okay, who says it's empirical? 1, 2, 3, 4, 5, 6. Who says it's theoretical? Who didn't raise your hand? You guys got it wrong. Okay? Yes, so this would be an empirical model. Why is it empirical?
Because they're measuring how often those numbers are reported.
We measured how often those things happen, right? Okay, so they just measured it, what is the census. They measured how often it happened. Okay? All right, so what if I said, find the probability that a person is not married? I'll bet you guys already know how to do this without me even telling you. How would you find out if a person is not married, according to this data? Arthur?
So I think first I'll you would sum all of the values.
Turn off that light. I think it's easier.
And then you would
Oh, what should that add up to? It should add up to 100%, does it?
hopefully it does.
Or one.
It does.
Okay, then you would just add up the three values. So 0.503
0.503
plus 0.003.
003 plus 0.42. Okay? That would be 0.548. Okay? Is there another way to do that that might be easier? Yes.
You could just subtract 0.452 from 1.
1 minus 0.452, and you would also get 0.548. Pretty cool, right? Okay? So a couple things that I want to point out here. So what Carson just told us here is called the complement rule. That's with an E, not an I. I'm not complimenting him on his correct answer, although I should. That was a good answer, okay? The complement rule says the probability of the event, and I'm going to put C for complement, equals 1 minus the probability of the event. Okay? One of the things that you will find is that in some cases it's easier to figure out the complement than it is to figure this out. This wasn't too bad. Sometimes it can be really bad though. Okay? Now, Arthur was correct, but he made an assumption. Okay, we didn't talk about the assumption that he made. Okay? So when we're talking about marital status, Arthur made the assumption that you're only in one of these categories at the time. Could a woman aged 25 to 29 be both married and divorced?
Yes.
Yes. Okay? So the assumption that Arthur made here was that these categories are mutually exclusive. Okay? Which means you can only be in one category at a time. Okay? So are men and women mutually exclusive? That's your question. Used to be. Okay? Are women and Democrats mutually exclusive? No, you can be a woman and you can be a Democrat, right? So that's definitely not, you could be both in that case. So women and Democrats would not be mutually exclusive. Okay? Heads and tails, is that mutually exclusive? Yes. So the way that Arthur did this, we are assuming that these are all mutually exclusive, which may or may not hold true. If we said current marital status, we could say yes, those are mutually exclusive. Okay? So, all right. So let's talk about some probability rules. Okay, number one, all probabilities must be between 0 and 1. I used to make a joke about the Browns. Cleveland Browns, they were so bad, I almost want to say the probability of them winning the Super Bowl was negative. They're not so bad anymore. Probably the Dolphins would be that bad now, right? Okay? You almost want to make it negative because they're so bad. But, yeah, it has to be between 0 and 1. Okay? All right, B, all probabilities must add to 1. Now, if independent. Okay? Now, that was one thing Arthur did right off the bat, which is they should all add up to 1. And they should if it's independent. Okay? Independent is different than mutually exclusive. Now, for example, I don't remember if I told you, but I think I did. On my master's project, I was working with a fertility doctor, and we were trying to come up with a method to do a confidence interval on an odds ratio for whether a couple would get pregnant. Okay? So let me ask you this. If a man and a woman have sex every day for 30 days, is she guaranteed to get pregnant? No. Okay? What does it, and I'm going to use this word on purpose, what does it depend on? What are some things that might prevent a woman from getting pregnant?
Infertility issues.
Infertility issues on her part or on his part, right? Anything else?
She has to be ovulating.
She has to be ovulating. Hopefully that happens within 30 days. Sometimes,
they're irregular.
sometimes they're irregular, right?
Yeah.
Okay? But there's lots of things. This plumbing might not work right. You know, she might have some, yeah. I guess we can call that fertility issues or whatever. Okay, so this is only true if we're assuming independence. So pregnancy would be, yeah, we depend on a lot of things, right? Okay? So yeah, we made that assumption that these not only are mutually exclusive, but they are independent as well. Okay? All right. We talked about here we see for the complement rule. Complement rule. Probability of the event complement equals 1 minus the probability of the event. And the if two events have no outcomes in common, you can add probabilities. Okay? All right, now, the one thing that I will say about probability, okay? I much prefer statistics probability. One thing that I will tell you is when I tell people, especially guys, that I teach statistics, one of the first questions, especially if they're a sports fan, is, hey, you can help me with my fantasy football team. And I'm like, yeah, I'm really not that much better than anybody else. I will tell you, I did have a guy at work, and I remember he was Mexican, and he didn't know that much about the NFL. And he would they'd have like 10 games listed there. And you had to pick the winners. I would always finish second. I could never finish first, always second place, picking the winners. But at any rate, so probability, I think, can be a little harder than doing the statistics, but every statistician needs to understand a little bit about probabilities. So one of the useful things with figuring out probabilities is what's called the sample space. Okay? The sample space is a list of all possible outcomes. Okay? One of my favorite problems to put on the test, because students are lazy and they would rather get the problem wrong than write out the sample space and get it right, okay, is a dice problem. What if I said, take 2 dice, find the probability that you roll a 9 or less than 4. Okay, now most of you probably don't know that off the top of your head. Okay? Does anybody know that off the top of their head? Okay, good, that's right. Okay, so here's how you can figure this out, but only if you want to get it right. Okay? List all possible outcomes. Okay? So you could roll a 1 and a 1. Or a 1 and a 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. I like to do that because some of you don't just were like, well, I'm just going to guess. You're going to guess wrong. Okay? All right. Some of you are going to say, well, the order doesn't matter on dice, right? The 2, 1 is the same as the 1, 2. Okay. Hopefully, we'll see if this problem, I just made this up, I don't know, but here's what I'm going to say. If you want to be sure to get it right, assume that order matters. Here's why. If you assume that order doesn't matter, you could actually split this just like that, right? Those are all the possibilities. Do you have the same possibilities above the line as below the line? Yeah. I don't think so. You got 6 and 5 is 11, and 4 is 15, and 3 is 18, 19, 20, 21. You got 21 possibilities above the line. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You only got 15 below the line. Okay? This is why all those gamblers back in the 1600s were like, we can't figure out why we're getting this wrong. Okay? Above the line, you've got 21 possibilities. You've only got 15 below, so we did not split that evenly. Okay? So I will say sometimes the order doesn't matter, but you should always assume the order matters, and then you'll for sure get it right. If you want to assume the order doesn't matter, you might get it right, you might get it wrong. Okay? All right, so I want a 9, right? I can get a 9 with a 6 or a 3, a 5 and a 4, a 4 or 5, and a 3 and a 6. So that's the first part. I can also want less than 4. Is 4 okay if I'm looking for less than 4? No. So none of these work. So I can go 3, 3, or 2. Okay? So the correct answer is all the circles, right? 1, 2, 3, 4, 5, 6, 7. Out of how many possibilities are there? 36 possibilities. Okay? Now, if I had assumed that the order doesn't matter, okay? Order doesn't matter, I'm going to throw out those, right? And so the wrong answer would be 1, 2, 3, 4. 4 out of 21. Okay? What's the percentage on these?
I don't understand.
Like, I get why you would do that.
Why, why'd you throw those ones
Okay, I threw these out because I said order, so 6, 3 is the same as 3, 6, right? 5, 4 is the same as 4, 5. 2, 1 is the same as 1, 2, right? Okay? So I'm throwing out all of these below the line. I'm doing it wrong on purpose. I'm doing it just to show you that it does matter. Okay? So if order doesn't matter, I've got 21 options and I've got 4 circles. Right? So this is the wrong way to do it. This is the way those gamblers back in the 1600s did it. And they said 4 out of 21, if I pull up my quick calculator here, equals 4 divided by 21. This works out to be 0.190476. Okay? That's what the gamblers who said, Blaise Pascal, we can't figure out why we're doing this wrong. Whereas the true answer was actually 7 divided by 36. 7 divided by 36, which is 0.1944. So they're close, but anyway, they're not the same. Okay? So if you think this is only going to happen 19% of the time, it's closer to 19.5% of the time. They're close, but this is actually the correct answer. Okay? Now, if we're doing this if this were a test question, I would much rather you gave me the fraction than the decimal. Okay? All right. So now, another thing that I may ask you to do here is, back here, hopefully you can see, is I may say, find the probability that you roll anywhere between a 2 to a 12. Find the distribution. Okay? So for example, what's the probability that I roll a 2 or a 3 or a 4 or a 5, 6, 7, 8, 9, 10, 11, 12? Okay? This is another way. So this is one version of the sample space where you're drawing each dice individually. This is another way to draw the sample space where you're drawing all of the possibilities you can get. Okay? Probability of rolling a 2 is 1 out of 36. Probability of rolling a 3 is 2 out of 36, etc. Okay? And so you should be able to fill out this table all the way to the bottom. Do we assume that these are mutually exclusive? Do we assume they're independent? Okay, so what should it add up to if I do it correctly? 36 out of 36 or 1, right? Okay? Now, let me give you another example of a case where people often get it wrong because they don't write out their sample space. Okay? Let's say that I want to flip a coin 3 times and count the number of heads. Okay? So if I flip a coin 3 times, I count the number of heads out of 3 flips. What is my sample space? What's all the possibilities?
No heads.
No heads, that's the one people usually forget.
All
We're studying
heads.
with Carson. So,
All heads.
all heads, so 3 heads,
One head.
1 and 2, right?
Yeah.
Okay, now a coin flip is equally likely heads and tails. Okay, would it be appropriate for me, if these are my number of heads, I'm doing a probability distribution, and the heads and tails are equally likely, can I just say, okay, it's 1/4, 1/4, 1/4, 1/4?
Where did you get 1/4 from?
4 possibilities, right? 0 through 3 is 4 possibilities. Is that correct?
No.
There's
No.
less probability that you're gonna get 0 and 3.
Okay, why is that not correct?
Because it's not like the marriage problem where it's gonna total up to 1 because,
Oh, it is gonna total up to 1. It should total up to
but
1.
it's because you're flipping the coin 3 times.
Okay, so let's draw out the sample space. 0 heads would be, that would be tail, 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 right?
Right.
How many ways can I get 1 head?
You can get head, tail, tail,
Head, tail, tail,
tail, head, tail,
tail, head, tail,
tail, tail, head.
tail, tail, head.
Hurts brain.
How many ways can I get 2 heads?
2.
Head, head, tail,
Or no, it'd be 3.
head, tail, head,
Tail,
tail, head, head. How many ways can I get 3 heads?
1.
One way.
Only 1 way, head, head, head. Okay? All right, so based on this, how many options are there?
8.
8 options. Okay, so my denominator's already wrong, all right? This is the wrong way to do it. It's got to be out of 8, okay? How many ways can I get 0 heads? 1 way. 1 head. 3 ways to get 1 head, right? 3 out of 8. How many ways to get 2 heads? 3 out of 8. How many ways to get 3 heads? 1 out of 8. Does that add up to 1? 3 and 3 is 6, 7, 8. 8 out of 8. Okay? This is the correct way to do it. But if you don't think about this and you don't draw, so you've got 2 different sample spaces here. You've got the number of heads, and you've also got the outcome of every individual flip. Okay? So once again, assume that order matters. Now you can look within this group, order doesn't really matter within the group, but you've got 3 ways to get that. So it's 3 times more likely to get 1 head or 2 heads than it is to get 0 or 3 heads. Does that make sense? Okay? So this is why those gamblers kept screwing up. They were like, oh, heads and tails are equally likely. This must be the correct probability distribution. No, it's not. Okay? These are much more likely than these. Okay? So once again, order matters. Okay, now I could actually take this, and since you guys still suck at making histograms, okay, I think I'm gonna have to put it on a test again. Maybe one of these days you'll get it right. Okay? How could I make a histogram out of this data?
So you would take those possibilities as categories.
Okay? Draw my graph here.
So like probability that it would be 0 would be
So do I want probability on the x-axis or the y-axis?
the x-axis.
Put the probability here.
Yeah, frequency goes away.
Okay, so I want to do a probability histogram. Okay, so I want the probability to be on the y-axis, not on the x-axis. Okay, what goes on the x-axis?
Wasn't it like a 0 went to the category? categories, right?
What are the categories?
0, 2.
In this case, it's just going to be the single numbers, 0, 1, 2, 3. Okay? So if I'm doing a probability histogram, there's two ways I could do it. I could do it in decimal form, but this makes more sense to do it in fraction form, right?
Yeah.
Okay? So the probability that I get a 0 is 1/8. A 1 would be 3/8. A 2 would also be 3/8. 3 would be 1/8. How would you describe that?
Or just numbers.
So it's like a,
You know, that would be unimodal, right? Yeah, you could almost say that's normal. It's kind of small though, right? Okay? Symmetric. Maybe we could call it symmetric. Okay? I should make you do this as a homework problem. Draw a histogram out of that. What would the expected values would be. Okay? All right. Okay. Now, let's talk about the law of large numbers. One of the things you'll notice about this is gambling is one of the easiest ways to figure out probability. We're going to talk a lot about gambling. Okay? Law of large numbers. I'm going to give you two definitions. I'll give you the fun definition first. Why the casino always wins and you don't. Okay, that's the fun definition. Okay? The casino wins because they understand the law of large numbers. But basically, a better definition is the observed gets closer to the expected as repetitions increase. Okay? Now here's what I mean by the law of large numbers, okay? You and I are going to have a bet, okay? We're going to bet on a coin flip, okay? We're going to bet $1, okay? So we're going to flip it 10 times. 10 times. Okay? Now we're lucky. It comes up, or I'm lucky, it comes up 8 heads, 2 tails. Okay, I'm betting on heads. How much, if we're betting $1 every time we flip it, how much are you down?
$10.
No, I won 8 times, you won twice.
So down $2.
So you're down, how much?
$8.
8.
I won 8, you won 2.
So you're down 6.
You're down $6.
Because you gave 8, but you got 2 back.
Yeah, right. You lost $8, but then I gave you 2 back, right? Okay. Now, does that seem like a normal turn of events here? What would you? How many heads would you expect?
5.
You'd expect 5 heads and 5 tails, right? We should have come out even. You're down $6, right? So you think, the quote unquote law of averages says it's going to go in my favor, right? Isn't that what you think? Keep gambling, I'm going to get that money back, right? Because it's not going to come up 8 heads again, is it? I mean, 80%, it's only supposed to come up 50%. It's going to be in your favor, right? Okay, we're going to keep playing. We're going to now flip it 100 times. Okay? It comes up, so this comes up 80% heads, right? Okay, we flip it 100 times, and here's what happens. Comes up 60 heads. Comes up 40 tails. What's the percent heads now? It's 60%, okay? That's closer to the 50% that you expected, right? Okay? So have the odds gotten better for you?
Yeah.
About half. How much are you down? You're now down $20. Okay? You were down 6, now you're down 20. Let's
Would
keep
you
playing.
start from the 6 though?
What'd you say?
Like, would you start from that you were already down 6?
Well, we just kept playing. Okay? We're just taking a snapshot. Okay, we're gonna keep playing. We're gonna do this 1,000 times. Okay? Now it comes up heads 550 times. And it comes up tails 450 times. Have your odds improved?
Yeah.
Good, because now it's closer, 55% heads, right? Law of large numbers is working. We keep repeating, we went from 80% to 60% to 55%, right? Odds are getting better for you. How much are you down?
100.
You're down $100. And the odds are getting better for you. This is why gambling's stupid. Do you know, why did they give you alcohol? Free alcohol.
To impair your judgment.
So that you keep doing this. Oh, it's coming in my favor. Look, it's coming in my favor. You're on this. We're taking even more of your money. Okay? This is the law of large numbers. The casinos understand this. It's why they give you free alcohol, because they want you to keep making stupid decisions. Keep playing. Stay at that slot machine. It's getting better for you. Okay? You see that? All right. Why the casino always wins. Okay, so let's do another example here. I think this is the last one. Let's see here. But before we do that, we do the myth of randomness. Okay? All right, we're going to flip a coin. And I want you to tell me which one is more random. One time we flip the coin and we get tail, 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 head, head, head. Okay? The next time we flip the coins, we get head, tail, head, tail, tail, head. Who says option number 1 is more random? Who says option number 2 is more random? 2, 4, 5. Who says they're equally likely? Raise your hand too quickly, right? Yes, these are equally likely. Okay? 3 heads, 3 heads, 3 tails, 3 tails. Okay? Humans are really bad at math, at probability. Okay? We see this and we say, oh, there's a pattern going on. Clearly that is not random. No, not clearly. Okay? So let me just tell you this. If a family has 4 girls in a row, does the quote-unquote law of averages that you keep hearing about, especially on sports, oh, law of averages, right? Does that mean that the probability of boy is higher for the 5th child? No. It's still 1/2. Okay? Listen to this. In 1986, Evelyn Marie Adams won the New Jersey lottery for the 2nd time. That's not right. Okay? The New York Times stated that the odds of winning twice were 1 in 17 trillion. It doesn't happen very often, right? However, 2 statistics professors said the odds of winning twice is tiny, but it is almost certain that someone will win twice. And they predicted that the probability that someone would win twice over the next 7 years would be 1/2. That seems pretty high, doesn't it?
Yeah.
Okay. 2 years later, in 1988, Robert Humphreys won his 2nd jackpot. Okay? Now here's the funny thing. There's a thing on the hidden brain, I'll have to find it. And they said, if you win the lottery once, you're more likely to win it again than the rest of us. Why? You got house money now. You got money to burn. You can keep entering, right? Because you got You won the lottery. Just keep going. There have been people that have won it like 4 or 5 times. Okay? So, all right, so that's what we call the myth of randomness. Oh, that reminds me, I do want to show you this thing. Oh, do I have that? I don't have that link anymore. I had a link to a news article that says, man struck by lightning moments after buying a lottery ticket. You're more likely to be struck by lightning than you are to win the lottery. So, all right, so the last thing that I wanted to do was, let's pick on, what did I pick on today? Rachel, who's your favorite, who do you want to go see in concert? Rachel has tickets to, please don't pick a country star. You don't know? You don't want to go to a concert? Imagine Dragons, there we go. I was going to say Lawrence Welk, I was pretty sure you didn't like that. Imagine Dragons. She wants to take, she has 4 tickets. She wants to take 3 friends. Okay, so Rachel's going. Okay, who wants to go with Rachel? Okay, so Kennedy wants to go. Who else? Arthur and Sabrina. Okay. So Kennedy, Arthur, and Sabrina want to go. Find the probability. Oh, she's only got 3 tickets. Oh, we'll do it that way. Yeah, we're gonna knock off somebody. We want to do that. Oh, she's got 4 friends. No, she's got 4 tickets. Who else wants to go? Jose, you want to go?
Yeah.
Okay. All right. So she can only take 3 friends. Okay. Find the probability that Arthur and Jose go. How would you do that? She's drawing it on that.
So you have to like write up all the different potential.
We need to do the sample space, right?
Yeah.
So what's the sample space? Kennedy, Arthur, Sabrina. Kennedy, Arthur, Jose. Right? Arthur, Sabrina, Jose. Arthur, Jose, Sabrina. Go a different order. We forgot about that, didn't we? Kennedy, Sabrina, Arthur. Kennedy, Jose, Arthur. Sabrina, Jose, Arthur. Sabrina, Arthur, Jose. I should have done this with smaller people. There's gonna be a lot of these here, right?
Why do you have to do that second row if it's like already 3 tickets to first?
Why do I have to worry about this?
Because they're already getting those tickets, so what's the point of rearranging the order with the same people?
That's right. What's the point of rearranging the dice? You don't want to get the problem right. Okay? Now, here's what I will say. Does the order matter? I don't know. Sometimes it does, sometimes it doesn't. If you want to get it right, pretend it always matters, and then you'll get it right. Okay? And will it be on this one? This one might be a case where it doesn't matter. You can only do half of them. But I don't want to be the gambler that gets it wrong. I want to be right. Okay? Now, so we started with, let's see, are there any other things we could start with, Kennedy? Anyway, so we can keep going. Kennedy, ASAJ, KSA, KSJ, KJA. Oh, we already got that one. KJS. Right, we don't have that one. And KSA, we don't have that one. Right?
No, we have KSA, we don't have KS. J, no, we have J.
KSJ.
KSJ.
You want to do these in a nice orderly way. So that we get this, okay? So we started with the A's, AS. I think there's another AS. Okay, ask. Okay, these can be a pain in the butt, can't they? Okay,
Is there like a shortcut we can use to see like what the total number should be? Like multiplication or something, like 4 times 4, or like, I don't know how you, like.
there is, I wasn't gonna cover that chapter.
Oh, okay.
I'm gonna try to keep this fairly simple. But, yeah, so let's keep going here. If we start with Kennedy, AS, KAJ, KSA, KSJ, KJA. I think we've got all the Kennedys, okay? Then we can go A's. We should have 3 more A's, right? ASJ, AJS, ASK, AKS,
AJK?
AJK, AKJ. Okay? SJA, SAJ,
SJK?
SKJ, SJK.
SJK?
I should be having 2 more here.
SJK, SK.
What is it?
SKA?
S, K, SJ, SA, J, S, J, A. Is that it? No, I got that one already.
SKA?
SKA, that's what it was. Okay? So I started with the K's, started with the A's, started with the S's, so I haven't started with the J's. J, S, A, J, A, S, J, A, K, J, K, A, and J, see, I haven't done an S.
JK?
JSA, JAS, JAK, JKA, J,
KS?
KS, JSK. Okay? The probability that AJ go. I got an AJ, 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 AJ. There we go. Okay, so how many options do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Got 24 options. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I should have 12. What am I missing? AJ. I'm missing something. Oh, there's an AJ. And where's the other AJ? Right there. There we go. 12 out of 24. Okay? And I could ask a lot of questions with this sample space now that I have it, right? What's the probability that, I guess, 2 girls go or 2 guys go? I guess we did 2 guys already. What's the probability that Yeah, I could ask lots of questions. Okay? So, quiz on chapter 12 is on Tuesday. So see you all on Tuesday. Oh, I don't know what to do. Oh, no, I wrote that whole thing and then put it on the board. There's your sample space. You guys are terrible cameramen. That's the bottom, top. That's the bottom. There it is. Okay, freeze frame.